Bismillah ar-Rahman ar-Rahim. The title of chapter 2 is Atoms, Molecules, and Ions. In the chapter, we'll start explaining some fundamental and basic chemical concepts. The chapter starts with these three fundamental laws. The first law is called law of conservation of mass. The second one is law of definite proportion. And the third law is here. It's the law of multiple proportion. Let's explain each one of them briefly. In law of conservation of mass, the law says that in any chemical reaction, let's say if you have a chemical reaction between A and B to produce C and D, then the total mass of A and B must equal the total mass of C and D. The total mass of reactants equal the total mass of products. Later, we will give you a specific example to illustrate this law. The second law is the law of definite proportion. This law says that for any given compound, let's say water or carbon dioxide or whatever, if you have a pure sample of any compound, let's say pure sample of water, when you analyze it, you will find that it contains a certain proportions, a certain composition of each element. In water, the percentage of hydrogen is 11% and the percentage of oxygen by mass is 89%. Now, if you have any other sample of water, pure water, not any water, pure water from wherever, from any other source, let's say the first sample from Riyadh and the second sample of pure water from America or from China or from wherever, then all of these three samples must contain the same percentages of hydrogen and oxygen, 11 and 89%. These percentages are definite and well defined within the same type of compounds. The third law is called the law of multiple proportion. Law of multiple proportion states that if you have the same type of elements, let's say carbon as an example, carbon and oxygen, then you can form a series of different compounds using the same elements. So if I have carbon and oxygen, I can form carbon monoxide and I can form carbon dioxide. According to law of multiple proportion, the ratios of the masses of the second element, which is oxygen in this case, combine with 1 gram of the first element, which is carbon, can always be reduced to a small whole number. Let's explain it. In carbon monoxide, for each 12 grams of carbon, you will have 16 grams of oxygen. While in carbon dioxide, for each 12 grams of carbon, you will find that they combine with 32 grams of oxygen. Now we can find the ratio of oxygen that can combine with 1 gram of carbon. How? Just divide over 12. So if 16 grams of oxygen combined with 12 grams of carbon, so if we can find the mass of oxygen that combines with 1 gram of carbon by dividing 16 over 12, which equals 1.333 grams of oxygen per 1 gram of carbon. Now in carbon dioxide, we can find the ratio by dividing 32 grams of oxygen over 12 grams of carbon, which equals 3 grams. 32, this equals 2.666 grams of oxygen per 1 gram of carbon. Now, when you divide 2.66 grams, the result of the second compound, which is carbon dioxide, over the result of the first compound, which is carbon monoxide, it will be 2.666 over 1.333, which equals 2 over 1. So the ratio between oxygen in the first, oxygen in the second compound, which is carbon dioxide, to the percentage or the ratio of oxygen in the first compound, which is carbon monoxide, is 2 to 1. So as you can see, we can always reduce it to a small whole number. Let me give you another example. Assume you have 100 gram samples of, let's say, two compounds, two different compounds. Both contains sulfur and oxygen as the only other component. After analysis, we found that the mass of sulfur in the first compound is 50 grams, and in the second compound is 40 grams. Explain how these data illustrate the law of multiple proportion. So here again we have two compounds of sulfur and oxygen. Let's say this is compound 1 and here is compound 2. In compound 1, 50 grams is sulfur and the total mass is 100 grams. Don't forget that we started with 100 gram sample of each. So the mass of oxygen in the first compound should be 50 grams. In the second compound, 40 grams is sulfur and 60 grams will go to oxygen. To find the mass of oxygen that combined with 1 gram of sulfur, we should divide 50 over 50, which equals 1. So what does it mean? It means 1 gram of sulfur combines with 1 gram of oxygen here in the first compound. Now do the same for the second compound. Divide 60 over 40, it will be 1.5. So it means that 1.5 grams oxygen combines or combined with 1 gram of sulfur. Now when you divide the result of the second compound over the result of the first compound, it will be 1.5 grams over 1 gram. This is compound 2 and here is compound 1. To convert it to whole number, ask yourself what is the integer or the whole number that converts these fractions to the smallest whole number. The answer is 2. When you multiply by 2, 1.5 times 2, it is 3. 1 times 2 is 2. So the ratio between them is 3 to 2. 3 for the second compound to 1 of the first compound. So again, here we ended with the reduced whole numbers, which illustrates the law of multiple proportion. Now let's give you this example here to discuss the law of mass conservation. If you have reactant 1 and reactant 2 with a total mass of them, let's say the reactant 1 is carbon monoxide and the reactant 2 is carbon dioxide. If you start with 56 grams of carbon monoxide of calcium oxide and 44 grams of carbon dioxide, then definitely the mass of the product should be 100.08 grams, which is the summation of the two masses. This example here illustrates the law of definite proportion, the second law. Here, let's say you have 20 grams of calcium carbonate, 20 grams of calcium carbonate, and you analyze this sample. You found that it contains 80 grams calcium 2.4 grams carbon and 9.6 grams of oxygen. So we can easily determine the percentage of each element in the compound by dividing the mass of each element over the total mass of the compound. So here the percentage of calcium in this sample is 8 grams over 20, which is the total mass, which is 0.4. Multiply it by 100% to determine the percentage or the value in percentage. It will be 40%. Do the same for carbon and oxygen. So you will find that it's 40% carbon, 12%, 40% calcium, 12% carbon, and 48% of oxygen. This is for this sample. Now, if you have any other sample of pure calcium carbonate, regardless the source of this sample, definitely you must have these percentages. Let's solve this example together to illustrate the law of multiple or the law of definite proportion again. Analysis of 84 gram uranium containing compound pitchblende. Pitchblende, this is the name of the uranium ore, yani the source of uranium. The name is not important. So analysis of 84.2 grams. So here, let's say we have a sample of pitchblende with 84.2 grams of pitchblende. Analysis of this sample showed that it contains 71.4 grams of uranium and oxygen as the only other element. So we can easily determine the mass of oxygen. Just subtract these two masses. So it's 84.2 minus 71.4. So the mass of oxygen is 12.8 grams oxygen. This is uranium, tamam, and this is oxygen. How many grams of uranium can be obtained from another sample of pitchblende? This is a bigger sample of pitchblende with 102 kilograms of pitchblende. What is the mass of uranium in this sample? So simply, here we have two samples of pitchblende, and according to law of definite proportion, we know that the percentage of uranium should be the same in both samples. We can determine the percentage by mass of uranium in the first sample by dividing 71.4, which is the mass of uranium, over the total mass of pitchblende, which is 84.2. Then the answer is 71.4 over 84.2, then it will be 84.8%. طبعا multiply it by 100%. Again, here, as both samples are pitchblende, then we can say that the percentage of uranium in the first sample equal the percentage of uranium in the second sample. So to determine the mass of uranium in the second sample, simply multiply the percentage of uranium, which is 84.8 over 100, this is the percent sign, times the mass of the second sample, which is 102 kilograms. The answer is 86.5 kilograms. Note that the unit is kilograms. Here we multiplied the percentage by kilogram. The percentage it doesn't have any unit. So when you multiply the percentage by any unit, then you will end with the same unit. Here kilograms. But the question asks you to determine the grams of uranium. So to convert kilogram to gram, as we have learned in chapter number 1, then you should multiply by 10 to the power 3 or 1000. So the final answer is 8.65 times 10 to the power 4 grams, which is 86,500 grams. This is briefly how these three laws are consistent with each other, and these information are basic because we will use them later during the upcoming chapters. Now let's proceed to the modern view of the atomic structure. As you know, atoms are the simplest building unit of any matter. In chapter number 1, we said that chemistry science is a fundamental science that focuses on studying the matter, and matter is anything has a mass and volume. Now, the big question is how or what is the basic component of these matter, how the different matters are built up. The answer is the different matters consist of the small building blocks, and these blocks are called atoms. In chemistry, all known atoms, all atoms we know, are arranged in something called periodic table. We will, inshallah, study it later in more details, how atoms are arranged in periodic table in columns called groups, and in lines or rows called periods. We'll explain all these details. But before that, let's discuss together very briefly how atoms look like, yani how they look like, and what are the subatomic particles, what are the components that we can find in each atom. Here, this picture illustrates a very simple model of the atom. I will repeat it here. In any atom, in the center of any atom, you can find something called the nucleus. This is the nucleus. It's a small sphere. In this nucleus, you can find two types of particles. The first type is called the protons, and the second type is called the neutrons, P plus and N0. P plus is, from the charge, you can conclude that these protons are positively charged particles, while the neutrons are neutral. This is N0. Here, or these particles can be found where you can find them in the nucleus. Now, outside the nucleus, you can find the third component of the atom, the third subatomic components or subatomic particles, which is called electrons. So here, these electrons, you can find them in a certain routes. These circles, these are energy levels. Later, inshallah, in chapter 3 or in chapter 7, we'll explain all of these energy levels. So the first circle, this is the first energy level, the first main energy level, in which n equals 1, and here n equals 2. This is the second energy level, third energy level, and so on. In these energy levels, you can find the third component, the third subatomic particle, which is electron. Here, each one of these energy levels and each atom contains a certain number of electrons that rotate around the nucleus in these energy routes or energy pathways. One more detail about the atomic structure. If you compare the diameter of the nucleus to the diameter of the atom, the diameter of the nucleus is something times 10 to the power minus 13 centimeter. So here is the nucleus again, and here is the atom again. Okay? If you compare the diameter of this nucleus to the diameter of the atom, it will be 10 to the power minus 13 centimeter. So it's 10 to the power minus 15 meter for the nucleus to 10 to the power minus 8 or 10 to the power minus 8 or minus 10 meter. 10 to the power minus 10 meter for the atom. When you divide these two numbers, you will find that the ratio is approximately 1 to 100,000. Sorry.